Welcome to the UltraScale Creating a Memory Interface Design Quick Take video. In this video you are going to see how to create an example design using Vivado and MIG. We'll use Vivado to create a project, run MIG GUI to generate RTL and constraints file for a specific memory interface configuration, generate an example design with the traffic generator, run synthesis and implementation, view the schematic of the design, and view summary reports like the utilization and power. This will show you a fast and easy way to generate your memory interface and controller portion of your design, and help you accelerate your design productivity with a MIG and its hardware verified IP library. Let's start first by creating a new project in Vivado. Let's call it project 6. It's an RTL project using Verilog, and we can choose the Kintex UltraScale family. Let's look at a -2 device. See here we've chosen the package, the -2 device, and the KU040. We can go directly to the IP catalog under memories and storage elements and invoke the memory interface generator or the MIG GUI. The first step is to pick what memory core architecture we're interested in customizing. We have several choices: QDR2+, RLDM3, DDR3, and DDR4. This will bring up the default, which is a data width of 8 bits and a frequency of 1200. You can see here the status. We also have the choice of supporting Axi4 interface on the user side. We can choose to do so for DDR3 or DDR4. And then we'll go through step by step through each screen of the wizard. The first thing is to choose the clock period. Right now the default is 1200 megahertz or 833 picoseconds. We can change that if we wish, and that will change the frequency, or we can go back to the default for the highest performance, 833 picoseconds or 1200 megahertz. We also have a choice to pick an input clock period depending on what our system is designed for. We can pick the 100 megahertz. This is the input clock to the design that will generate the 1200 megahertz. We have a choice of components here. We can pick a by 8 or by 16, and then we can choose the width of the data bus. Let's pick 32. And in terms of addressing, we have the choice of picking the row, bank, column, or other combinations. The most commonly used one is the bank, row, column. Let's choose that one. We have options here for the cast latency or cast write latency. And then on the next screen we will see that we have a choice for using internal VREF or not. Let's stay with the default of internal VREF. Will save us I/O pins. And we also have the choice to generate debug signals. These debug signals are useful because they will tell us the various states that we're in as we implement this on the board and we monitor the activity. Let's enable that feature. Additionally, we have the choice to generate other clocks from the same MMCM used in the generation of this memory core, and we have a choice of generating different frequencies. The next screen is the bank planning screen, where we have a default assigned by the wizard in terms of the I/O banks. And here we have the granularity at the byte group level. And we can choose to assign the DQs or addresses in these banks. Different banks are different byte lanes. So we can, for example, unassign the address and control and assign them differently, as in this case. And as you can see here, as we are going through this process, the I/O planning status changed to partial, and as we assign the lost address and control, it's becoming complete. There is an error window that will point out if we make the wrong assignment, and for example, let's say we unassign this address and we assign it in this location, we will get an error saying that the address bytes are spread in more than one bank. So in this case, we can go back, unassign it, and properly assign it, which will give us the complete status. Let's move to next. Now, an additional feature is the ability to do the pin planning per pin and actually invoke the MIG I/O planner, which will give us the granularity at the pin level. Let's do that. Let's maximize the pin planner and take a closer look where the pins have been assigned. We can look at the I/O ports or the package pins. The package pins will tell us where we assigned by looking at the available pins. We'll see here that bank 44 has partial assignment, and bank 45 is almost complete with some additional pins assigned in bank 46. So if we look at bank 46, we'll see that there are several pins assigned there, and these are part of the debug signals, the calibration complete or data capture error, as well as the system reset. In bank 44, we'll see that what we have here is the two data byte lanes that we assigned previously. As we move to the other screen, the I/O port screen, we can actually take a look at the individual signals and how they're assigned. Clock enable, chip selects. We do have an option here to make changes. However, as we make these changes, we need to check their compatibility to the guidelines for the IOs as well as the IP. So there is a function here called report DRC. We can run this to see if there are any errors, and of course there are none because we haven't made any changes, but this is, we can try to pick some of the IOs available, and as we do this you will see that there are changes made here, and we can do a report DRC, and immediately we will get an error if we made a mistake and we have not actually assigned it correctly. So we can go back and discard changes and go back to the default in this case. Let's move on to the next stage, which is the configuration summary, where the wizard will show us what we have assigned. A quick summary of the clock frequency, the components that we're using, and if we're using internal VREF. Click OK, and this will basically close the MIG GUI wizard, and we'll start customizing the IP. We can go ahead and generate the IP. Next step is to actually generate an example design that includes a traffic generator and be able to synthesize and implement the design. So I have invoked the open example design. We'll start a script to generate a different project that includes the traffic generator. This is the example design. See here at the example top. Let's run synthesis. We can run implementation now. So we've completed the implemented design. Let's take a look at the elaborated design. This is a schematic view, which is useful to understand some of the building blocks. This is the MIG controller showing the output to the memory interface, the signals, as well as the interface to the example test bench. The test bench is supplying the stimulus to the user interface of the memory controller. is shown here with various signals. We also have the debug core, the ILA core, and this generates signals externally to monitor like the data compare error. Let's take a look now at some of the reports. One of them is the report utilization. This is an overview of the utilization. You can see approximately 8.2 kilowatts are used, and we're also using some memory internally. We can expand and take a closer look at some of the statistics here of the utilization. We also have a power report. This will do a power analysis and report the actual power. It's a quick summary with various building blocks and the power they consume. In summary, you have seen today how to build custom memory interfaces with MIG, how to use Vivado to quickly and easily generate the memory interface and controller design, and how you can accelerate design productivity with MIG and the hardware verified IP library. Thank you for watching.